Okay, end of chapter 14 questions. First question is about number 17, where in number 17 you're given some data and you have to figure out the order of the reaction and the rate constant. So we know, based on the information we're given, that the rate law is going to look like this, that rate is equal to some constant k times a raised to some power times b raised to some power. Okay? So if we're trying to figure out the power of a, we have to find two experiments where a changes and b doesn't. And that's going to be experiments 3 and 1. A, in experiment 3, the concentration is 3. And in experiment 1, the concentration is 1.5. So that's doubled. And then we compare those rates. The rate for experiment 3 is 0.640. I'm just taking it out of scientific notation. And the rate for experiment 1 is 0.320. And so I can see that that doubles. 2 raised to what power is 2? So that tells us that x is equal to 1. And then to figure out what y is, we've got to compare experiments 2 and 1. In experiment 2, b is 2.5. Experiment 1, it's 1.5. And the rate is going to be 0.32 divided by 0.32. Okay? 0.32 divided by 0.32 is 1. And then, I wrote this wrong. 2.5 divided by 1.5 is 1.67. 1.67 raised to what power gives you 1? Well, anything raised to the 0 power is 1, so that tells us that y is 0. So what that's telling us is that the rate law looks like this, that rate is equal to some constant k times the concentration of A. Now, to figure out the rate constant, we just pick any experiment and we take the rate and we divide it by the concentration of A. And that's number 17. And then, number 21, determine the order of the reaction. Okay, we're given some data. Here's what I did. We're given this data. And that's times. And then we're given some pressures. And so we can calculate some rates. Because a rate, we know it's the change in the concentration. In this case, it's going to be the change in the pressures over the change in time. So, the rate here, if I take 400 minus 316 divided by the change in time, which is 2,000, I get 0.042 for a rate. And then if I compare this change, 248 minus 196 divided by the change in time is still 2,000. I get 0.026. Okay, and then there's more data. I can calculate a rate here. 155 minus 122 divided by 2,000. 0.0165. Okay, well, Then I'll look at this. This pressure here, this is essentially doubling the pressure. I mean, 196 to 400, it's like from 200 to 400. And when you double the pressure, the rate doubles, just about. That tells me it's first order. Okay. Also, what I can do on that one is you could graph the information. Let's see. And to figure out that it's first order, you would actually graph the natural log of the pressures versus time. And so that means you'd take the natural log of these numbers and plot it on the y-axis, and then you would plot the time on the x-axis. And when you do that plot, it's going to give you a straight line, which tells you that it's first order. Okay, so either of those methods would work for that one. And then the slope could tell you the rate constant, okay? Or you can solve for the rate constant using this formula, that the natural log of AT is equal to negative KT plus the natural log of A0. And the concentrations are going to be at initial and final. So I'm just going to use, you can pick any 2 points of data, but I'll use these. So the natural log of 316 is equal to negative K times the time here is 2,000 seconds. It's the natural log of 400. And I'm going to solve for K. Natural log of 316. And for K, I get 1.18 times 10 to the minus 4 s to the minus 1. That's number 21. All right, what is the half-life of a compound of 75% decomposes in 60 minutes? If you're going to assume first-order kinetics, first order, we know that half-life is equal to 0.693 divided by K. Okay, and we're calculating the half-life, but we need a rate constant, and we don't have that. But we can calculate a rate constant using the same formula that we just used in the previous problem. Okay, and it looks like it doesn't give us an initial and final concentration. Okay, we're going to calculate K. The problem gives us 60 minutes. But it does give us an initial and final concentration because it says 75% has decomposed. So what that means is that if we start with 100, if 75% decomposes, then we end with 25. Okay, and we're going to just solve that for K. And for K, I get 0.0231 minutes to the minus 1. Now I'm going to take that over here and plug it in. And I get a half-life of 29.9 minutes, which is essentially 30. Okay. Then number 29. Okay. Number 29, it tells you it's second order, and so you're going to use this formula, because this formula goes for second order. And it's got two parts. Starting with a concentration of 0.086, so that's the initial. Calculate the concentration, so this is what we're calculating. After 22 seconds, so time is 22 seconds, and it gives us a K of 0.80 M minus 1 S minus 1. Okay, we worked one similar in class. I'm doing the right side of it first. So I've got 1 over AT is equal to 29.227, etc. But I need to take the reciprocal of that to solve for A, T. And the reciprocal of that is 0.0342 molar. That's 29. And 31. Again, it tells us it's second order. Okay. And so if it's second order, we know this, that the rate is equal to some constant K times the concentration of P squared, because it tells us it's second order, and the only reactants are P. So it has to be P squared. It gives us the rate constant of K of 6.2 times 10 to the minus 3 M negative 1 S negative 1. And then it says if the concentration of the protein is 2.7 times 10 to the minus 4 molar, well, that's got to be squared, calculate the rate. Okay, so that'll calculate the rate. .52 times 10 to the minus 10 molarity per second. And then it says how long will it take to decrease the concentration of P to 2.7 times 10 to the minus 5 molar. You're going to use this formula again. Okay, and that's the chapter 14 questions. Chapter 15. Chapter 15 gives you the equilibrium concentrations, and then it gives you two different reactions to calculate the equilibrium constant. Well, if we use A, the equilibrium constant is products, the ammonia squared. It's products over reactants raised to the power of the coefficient, divided by the nitrogen times the hydrogen. And the exponents are coming from the balanced equation, okay? And so that's what you would calculate for A. And for B, you could either take those numbers and do 0.25 divided by the nitrogen raised to the 1/2 power and the hydrogen, raised to the 3/2 powers, or if you recognize, and I mean, you'd recalculate that, But what's happening from the reaction in A to the reaction in B is all the coefficients have been cut in half. So whatever we calculate for A, if we cut the coefficients in half, that means for B, we take the square root of this number, and that'll give us the answer. If you double the coefficients, you square it, but if you cut them in half, you would take the square root of that number. All right, 29. All right, it gives us ammonium carbonate. Decomposes as follows. Okay, starting with only the solid. Okay, so this is a solid, this is a gas, this is a gas. At equilibrium, the total pressure, so the pressure of all of this is 0.363. So if the total pressure is 0.363, that means the sum of them. Total would be the sum of them. That means that the pressure of the CO2 is 0.121, and the pressure of the NH3 is 0.242. Those are atmospheres. Because, see, that would total to be 0.363, and I'm getting that from the coefficients. Okay, and so we calculate the equilibrium constant, the Kp. Well, Kp is products technically it's not in square brackets because it's atmospheres, but I'm just so used to writing it in square brackets. So that's how you would calculate the Kp for that one. And then 41. We're given this reaction. Hydrogen gas. We're told that the Kc is 0.534. And we want to know how many moles of hydrogen are present at equilibrium if a mixture of 0.300 moles of CO and 0.300 moles of water are heated in a 10-liter container. Okay, well, clearly, to reach equilibrium, we're going to have to use the products and make the reactants. And we're not given any numbers, so we're going to use X and make X. This is going to be XX, 0.300 minus X, and 0.300 minus X. We're given a Kc, so the Kc, 0.534, is equal to products, 0.300 minus X, times 0.300 minus X. So I'm just going to write that like so. Over reactants, and X times X will be X squared. And y'all know how to start this. Start by taking the square root of both sides. And I get 0.7308. Cross multiply, so that means multiply both sides by X. And then I'm going to add this X to both sides, so I get, and I'm showing more of this than is necessary. For the math, I'm just showing some steps. So X is equal to 0.173. What does it ask for? The moles of hydrogen present. So that should be 0.173. What is this? 15.